Good afternoon, everyone. This is the live session for the week 7, in which we will discuss 6 questions. And in this, we will focus mainly on the lumped mass system and the continuous mass system, like equivalent single degree of freedom system. You can say is like if we have like in the reality we have 3 story, 4 story, then how to convert it into the lumped mass system, or we consider it into the continuous system. So for this, we will solve some examples related to this. Okay. So in this, the first question is related to the what is the equation of motion for the system shown in the figure. Like we have given a system in which there are like initially first in the first half, in the first 6 sessions, you see there was only one mass. Now here two masses are there, like one mass of this rod and the another is the mass below it here. So we have to generate the differential equation for this kind of system. So for this kind of situation, we have to consider the mass, both the masses, like mass for the rod and the mass for the block. Okay. So now first to generate or develop the equation of motion, we need to make a free body diagram. We need to make a free body diagram of the system. So the first, if we make the free body diagram of the system, so let us we given a deflection, dynamic deflection, like the dynamic response, we give a deflection theta here. If we give a deflection theta, then the inertial mass of this rod, there is a inertial mass of this rod. So you can calculate if a bar is like rotate, then what will be the inertia of the mass. And we have a stiffness force to the spring, which is resisting, which is this one. So if this is a theta rotation, so what would be the this distance? That would be the theta into L by 2. And what will be the my stiffness force, which will be K into L theta by 2. Now if I am giving the deflection to this rod, there is a deflection in the mass also, in this mass. So that mass also displaced from this position to this position, says, like we consider here the center of this mass. So if we take the center of this mass from this, so that is 9L by 8. So the vertical movement of this mass block would be the 9L by 8 into theta. So the inertial force due to this mass in that direction also, and there is an inertial force due to some rotation also of this block. Like if I rotate, then if I take this mass, if I displace this bar at theta, then this mass also try to rotate. So to resist this, there is an inertial force due to rotation of this mass block about this center of the block. So that will be the m theta double dot, you can say, like that rotation can be m theta double dot. So we will write the equation of motion. So for this, first we calculate the inertial rotation, inertial mass of the rod. So mass of the about the hinge, what will be the inertial mass? That will be the about the center. If I have a rod like that, if I have a rod and the about this center, that is the ml square by 12. Okay. If I take about this end, which is L by 2, so that will be the parallel equation theorem, parallel axis, ml square by 12 plus m into L by 2 minus 0 square. So that will give me the ml square by 3. Now the inertial mass of due to the vertical movement of the plate, so that is the plate, or you can say block, whatever you want to say. So due to theta rotation, like the vertical displacement, which I have told you, like that will be the 9L by 8 into theta. Okay. So the vertical force developed in this mass multiply with this the acceleration. So if this is by the displacement, so acceleration I will double differentiate it. So that will be 9 L by 8 into theta double dot. So that is the inertial force due to the plate in the in the vertical direction. Now the rotational inertial mass. So inertial, sorry, initially I told you that I'm theta double dot. So now for the plate, the rotation of the plate about the center, which will be what will be the m by 12 into b square plus t square. So the dimensions of the plate are b is equal to l by 2, l by 8 plus l by 8. So that gives you l by 4. So this is L by 4 square, L by 4. So if you solve this, so that will become the ml square by 96. So this is the inertial mass, and what will be the uh, inertial force ml square 96 into theta double dot. Okay. So now we will write the equation of motion. Like we have the all the steps: inertial mass, stiffness force, damping force. So and the stiffness force which I have told earlier, that displacement is L theta by 2. So that would be the k into that displacement, which is L theta by 2. Okay. So this is the stiffness of the force. Now we are going to take the moment about this hinge in this diagram. If we take the moment about the hinge, so that will be the moment about the hinge, that will comes out to be I bar theta double dot for this bar. So I for this bar, what was the I bar? Ml square by 3. I plate, that was the force in the vertical direction. So that force, what was that force? That force was m into 9l by 8 into theta double dot. That was the force. Multiply with the 9l by 8, which is the distance. And I plate inertia of the plate about the rotational. So that was the ml square by 96. And this is the stiffness force. That was the k into L theta by 2. Okay. And this is the p force pt which is acting at here. So that will be the center to center distance from the hinge to this, that is a 9l by 8. So if you put this value of I, value of I plate, value of I plate rotational, and then rearrange the terms. Now if I will rearrange the terms, I get my equation of motion in terms of theta by considering the this mass as well as this mass. Okay, this is the simplest question. Now we are moving to the some typical question. Okay, like this kind of example also is given in your week 7 assignments. So if you get understand this, then you can solve it easily that problem also. That is the same nature of problem. Okay, now move to the another question. A uniform 5-story frame with rigid beam is subjected to ground acceleration UG double dot. All the floor passes are m and the stiffness is k. The shape function is shown in the figure is given us. What is the value of natural frequency omega n, where k is your 10 into 10 raised to power 5 Newton per meter, and the mass is 500 kg. So this is a kind of lumped mass system. So for the lumped mass system, we require first find out m equivalent, k equivalent. Then if we know m equivalent, k equivalent, what will be the my frequency? That will be the omega n is equal to k by m. Okay. So for determining the m equivalent and k equivalent, or say some says m dash, k dash. For that, I required first what is my shape function. So shape function is given in this for all the story. Sumer, can you mute your mic?
Yes, sir.
Okay, thank you. So in this, like the shape function is given to you, we have to find out the m equivalent, k equivalent. So the shape function is given as 1 by 5, 2 by 5, 3 by 5, 4 by 5 and 1. Like it is a linearly variation. So this is for the first story, this is second, this is third, this is fourth, this is fifth. Okay. So now for the generalized mass or the equivalent mass can be determined as the formulation for the lumped mass system is m dash is equal to summation I is equal to 1 to n mi psi I square. Here I is the number of story. So try to calculate the equivalent mass with the m is given to you 500 kg, the same, and the k is 10 raised to power 5 Newton per meter. So now initially you can find out in terms of m. We can in the at the end of the calculation we can put the value of the m and k. So if you put the value of shape function or calculate for this, so that will be the m, like m is a common in the all the stories. So I have taken it out and I have square of each of the shape function for the each story 1 by 5 square, 2 by 5 square, 3 by 5, 4 by 5, 1 square, and after solving I get the 11 by 5. Now same I have to determine the generalized stiffness, which is given as k is equal to ki psi I minus psi I1 minus 1 I minus 1 square. So for this the stiffness is also same for the all the stories. So first like for I have taken cages out, and the for the like for the first story I is equal to 1, and this term become as a 0, like the base. So at the base what is my deflection, what is my, like it is a rigid, so it is a 0 kind of. So that will be the 1 by 5 minus 0. For the second case, second story, that would be the 2 by 5 minus 1 by 5. For third story, 3 by 5 minus 2 by 5. So this is the same, like you can repeat up to fifth story. So after getting this, I put the values which I have told you, like 1 by 5 minus 0 square, 2 by 5 minus 1 by 5 square, same one up to fifth story, and after solving this I got this as a k by 5. Now I will get the omega n, which is given as k by m, square root of k by m, and I will put these values in this. So I got this expression, square root of k by 11m, and k value is given as 10 raised to power 5, and the m is given as a 500. So I got my natural frequency as a 4.26 radian per second. So this is the solution. Is there any doubt in this question? Anyone? Anyone have any doubt? If not, then we are moving to the another question.
1 minute, sir.
Yes,
Hello.
yes, yes.
Uh, Sir, I want to ask whether shape function is the relative uh, position of the mass, na? Total mass.
Yeah, shape function is related to the story of mass. Yes.
Ratio of
Ratio.
mass on the one story upon total mass, na?
No, no, that was the deflection. Like the shape function is the, like I have normalized it. Like shape function, like the deflection at the top. Like some says 10 mm is the deflection at the top. At the deflection of this, I have says 9 mm. At the deflection, I says 8 mm. Deflection, not the mass. And then
Okay, okay, deflection.
yes,
Okay,
that is the deflection. Like in some short of questions they are saying like deflection is the proportion of your story shear, that
okay,
depend on the
huh.
story shear. Story, from the story shear we can calculate the deflection. Mainly it's totally related to the deflection. not the passage and all the other things. These are the like other parameters.
Okay.
Okay. So now we are moving to the another question, which is also related to the lumped mass system. In this, a three-story frame is given to you. Mass of the each story is given, like the first story and two story given as a mass m, and the third story is given as a m by 2. And in this question, the shape function is given to us as a deflection due to the lateral force that are equal to floor weights. Like we have to calculate the deflection due to the whatever the force, like the whatever the mass is present here, we have to calculate the lateral deflection, and then we have to calculate the shape function. And after getting this, we have to determine the floor displacement, story shear, and the overturning moment at the floor and the base due to the ground motion characterized by the design spectrum, which I will provide later in this question. And that ground motion is scaled to 0.25 g. Okay, so now our first task in this question, we have to find out the shape function. So for the shape function, we determine the stiffness of the columns, stiffness of the story. So for the one column, for the like says this like the this any column which is fixed at the both the end, what will be the my stiffness? That will be the k is equal to 12 ei by lq. So for the two column, I will multiply it with the 2. That will be the 24 ei by lq. So for the first story, my ei is ei by 3. So for the first story, that will become as a 24 into ei by 3 over lq. So that will become as a 8 ei by lq. So in the second case, my stiffness is doubled. So that will become as a k2 is equal to 16 ei by lq. And in the third or the first story, this one, that will become as a 24 ei by lq. Okay, so in this, let us suppose this is equal to k something. So this is the calculation for the stiffness of the third story, that is a 3 i 80 I by lq, which I have calculated it here, and which I have denote it with the k. Now the stiffness of the second story, which will be the 16 ei by lq, which is also 2 time of the third story. So that is denominated as a 2k, and this is also 3k, denoted as 3. And now I want to find out what will be my k. So k is 80 I by L cube. If I will put the value of the E is given me as a 2 into 10 raised to power 11 Newton per meter, and the I is given as a 16,000 centimeter for power 4. And length of the like the height of the each story. Here length is related to the height. This is my L. Okay. So if I will put this, I can find out my K. So K value is 15 into 10 raised to power 6 Newton per meter. So now with the using this, I can say stiffness of this is K, overall this is 2K, this is 3K, and that value I will put later. Okay. So now we come to the shape function of this three-story frame. In this, they told that the shape function is due to the whatever the mass is there or the weight is there, the shear is developed due to this mass, and that due to that shear there is a deflection, and considering that, calculate the shape function. So for this, like in my story, like that is m m by 2, or you if you will multiply it with the g, that is the w by 2 weight, that is w, again that is w. So if that is the w is the weight or the force, like considering this is the force applied at that point, this is the force applied at that point, this is the force applied at that point. So this is w by 2. So what will be the my shear rate here? That will be the w by 2. What will be the my shear rate here? That will be w plus w by 2. And what will be the shear rate here? That will be the w by 2 plus w plus w. Okay. Is there any doubt in the stories calculation of the stories here? If you calculate the stories here, like we calculate in the third story, that is w by 2, In the second, it is 3W by 2. In the first, it is the 5W by 2. Now the story drift, like the we have to calculate the story drift. So, what is the stiffness? We have like the for the each story. For this, third one is K, second one is 2K, and first one is 3K. So for this story, if my shear force is W by 2, so what will be the drift? That will be the W by 2 divided by the K. For this, what is my shear? 3W by 2 divided by 2K. And for the first one, that is the 5W by 2 is the my shear, and the story drift is 3K. So that will be the 5W by 6K. So this is the story drift, like deflection of the each story is given, like this deflection, and this deflection, like this way you can consider. Now we have to calculate the overall deflection, like the deflection of the first story is same. Now the deflection of this story, what will be the, like that deflection also add in this. Okay, and in the third story, the total deflection will be the add of the deflection of the story 2 plus deflection of the story 1. So for the deflection of the first story is whatever we get is same, 5W by 6K, that will be the same. Deflection of the second story, both them plus total deflection, 3W by 4K and 5W by 6K, that will come out to be 19W by 12K. Now the deflection of the third story, that will be the plus this plus this. So total deflection at the third story, it will be the W by 2K plus 3W by 4K plus 5W by 6K, that will come out to be 25W by 12K. Now we want to get the, like we get the deflection. After getting the deflection, we can calculate the shape function. So here we are considering like the maximum deflection is here 25W by 12K. So if I will divide 25 by W 25W by 12K to each deflection, I will get the shape function. So I divide it by this, like all the shape function divided by this, like the top most deflection, which is the maximum. So I get this one, obviously that is the same. So that coming out to be 19 by 25, that is 2 by 5. So this way I calculate the shape function. So this is the 2 by 5, 19 by 25, and 1. After getting the shape function, now we need to calculate equivalent mass or the generalized mass, generalized stiffness, generalized load factor, and then we can calculate the time period. After getting the time period, we can get the SA by G from the response spectra. From SA by G, we can calculate the deflection of the story. From the deflection, from the deflection, we can get to the acceleration, and then we can calculate the shear. Same for the like the movement. This way, like first you calculate the generalized mass and stiffness, then other parameters are same, which we have discussed in the week 6, like the equivalent single degree of system we have considered. Generalized mass, whatever I have discussed in the previous question, that is the m is equal to summation I is equal to 1 to m I psi I square. So that will become as a, so here like I can, this is I have write W by Z. So no need to write W by G because we have given already m. W by G is what? That is the m. Okay, so that will come as a 1.2376 m. Now the generalized stiffness, same procedure what we have discussed in the last question. So say write the 3K 2 by 5 minus 0 square, 2K 19 by 25 minus 2 by 5 square, plus K 1 minus 19 by 25 whole square. So that is coming out to 0.7968. Okay, now after calculating it, and also a generalized excitation factor, that coming out to be summation of mi xi I. So if you also put this value, so you will get the factor 1.66 time m. So now the calculate the natural frequency. So natural frequency, what is your natural frequency? That is omega square, omega is equal to square root k by m. So k is, what is your k value? That is 0.7968 k, and what is your m value? M equivalent 1.2376 into m, and what is your m? M is given to you 50,000. Okay, and the k we calculate initially in the first slide, that was the ATI by L, from the ATI by L cube. So that is 15 into 10 raised to power 6. So that is the my natural frequency, 13.89. Now calculate the time period. Time period is coming out to be 2n. Tn is equal to 2 pi divided by the omega n, which is coming out to be 0.452 second. Okay. Now after giving the time period, we can also calculate the one of the generalized load factor, which is the excitation factor divided by the generalized mass, that is 1.66. We have calculated this one, and there is a 1.36 which we have calculated in the previous slide. So that is coming out to be 1.341. Now after calculating the load factor, like these nominations, if you have gone through the week 7 content on the NPTL, you will understand what is why I calculating these nomenclatures, these constants. Okay. So if you calculate the now the peak value of the acceleration at Tn is equal to 0.452 second, my SA by G. So can you tell me at Tn is equal to 0.452, what will be the value of my SA by G? Anyone from this graph? Anyone?
That would be the slope of the between 1 and 10, the 1.80 Tn inverse multiply by, so
Uh,
it is like that na,
no, no.
multiply.
Like first look the what is the range. So in this range, if you will look at my period is 0.452. So that period range is in this range.
To 2.71.
So only my SA by G would be the 2.71. If my period would be the higher than the 0.66, then my SA by G would be the 1.8 divided by the TM. That would be my SA by G.
Okay.
So at Tn is equal to 0.452, my SA by G is coming out to be 2.71. Now after getting the SA by Z, the also in the question they have mentioned that the peak response is scaled to 0.25G. So if we multiply this with the 0.25, so that is coming out to be 0.6775 SA by G. So from this, the spectral acceleration coming out to be multiplied with the G, so that will become as a 6.646 meter per second square. So now we can calculate the spectral deformation. So that is coming out to be d is equal to a divided by the omega n square. So omega we have calculated 13.989 in the previous slide, and the acceleration we got from this. So what we get over spectral deformation is the peak deformation, 34.44 mm. Like this is my story. So the peak deformation, that is the maximum deformation. Like first we calculate the d, so peak deformation coming out to be z naught multiply with the shape function into d. This is my dynamic displacement. So from the multiplying with the shape function, we can calculate the shape function at the different location. So the peak displacement is coming out to be this, and also multiply with this factor, we have calculated the load factor also, that modifies the equation. So that is the 1.341 which we have calculated. So that deflection is become as a 46.2 mm, and my floor displacements are become as a u naught is equal to load factor gamma into shape function gamma, sorry, not gamma, multiplied with this t. So sorry, that will be the z naught. So if I multiply with this the 46.2, so I get the this displacement. So this is the deflection at the top is the 46.2, this is the 35 mm, this is around 18.5 mm. This is the floor displacement, peak displacements of the floor. Now after getting the displacements, we need to determine the base shear or the shear in the floors and the movements. Okay. So now come out to the shear, storage shear. So for calculating the storage shear, first we need to calculate the floor force here or the equivalent static force. Like what will be my equivalent static force at here, at this point, at this point. If we will find out the equivalent static force, then we will able to find the storage shear. So first find the equivalent static force. So for the equivalent static force at the jth floor, the formula is given as a gamma, mass of that particular floor, psi is the shape function of that particular location, and the a is the acceleration. Like the force is, what is your force? Force is the m into acceleration, mass times the acceleration. So mass of that particular floor, and the a is the acceleration of that particular acceleration what we have get from the response spectra, and that response spectra is changed throughout with the gamma factor, load factor we have calculated, and that shape function corresponding to that location. Okay, so first calculate the shape, this one f1. So gamma is the same for the all the three cases. F1 mass would be the same, only thing it changes the shape function, that is the 2 by 5, and the acceleration is same, 6.6. So these three terms are same, only the this one is changed. So f1 is coming out to be 174.6 kilonewton, f2 is coming out to be 338.66 kilonewton, and the f3 is coming out to be 222 222.807 kilonewton. So these are the my static equivalent static force. Now after getting these equivalent static force, can you tell me how can I calculate the shear? Can you calculate the shear force if you have these terms f1, f2, f3? Anyone? Like, can you tell me what is the shear force in the third story? Okay, so what will be the my shear in this third story? The shear would be the whatever the force is there, f3. The shear in this, that would be the f1, f2 plus f3, and shear in this third story, f1 plus f2 plus f3, like summing of all these steps. So the shear force in this first story, that is the 175 kilonewton. In the third story, f2 plus f3, that is coming out to be 5.2.2 kilonewton, and the shear force in the third story, that is coming out to f1 plus f2 plus f3, that is coming out to be 736 kilonewton. Now after calculating the shear force, we are now moving to the bending moment calculation. So for the bending moment calculation, we have directly the static force. Now can you calculate the bending moment with these static force? Anyone? Like you have given the static forces. If you have given the static forces, so the bending moment at this floor, what would be the bending moment? This is my f3. So what will be the bending moment at this f3 time this height, which is 4 meter? What is my bending moment at this floor? That will be the f3 time 2 into that floor height h plus f2 into h. And what is my moment at the base? That would be the f3 times 3h, f2 times 2h, and f1 times h. This way I can calculate the bending moment. So overturning moment at the base, or the moment at the base, that is my f3, that is my f2, that is my f1. So sorry, that would be the calculation mistake. That would be the 12 here, and that would be the 4. like f1 multiply with the 4, f3 multiply with the 8, f3 multiply with the 12, and then you can calculate. There is some sort of mistake, you can calculate. Can you calculate? Can you try it? Bending moment at the first floor. So what will be the first floor at this floor? Says this, that will be the 338 into multiply with the 4, and f3 multiply with the 2h, so that will be the 2751 kilonewton meter. And the bending moment at the second floor, that is 174.6 into 4, that is 698.7. So bending moment at the, can you tell me what is the bending moment at the base, like in this calculation? So that will come around 371.8 kilonewton meter. Is it okay? In this question, is there any doubt? Anyone? Anyone? Sumit, do you have any doubt?
No.
Okay. If not, then we are moving to the another question. Now these three questions are related to the lumped mass system. Now we will discuss the questions related to the continuous mass system. For the continuous mass system, like first we need to determine the shape function. Like for the continuous mass system, how we determine the shape function? So if you have given a simply supported beam with the UDL, load W. So for this loading, can you determine the shape function for the continuous system? For the continuous system, like if we need to determine the shape function, how can we calculate? So let us try. Let us take a distance, take a section at x section, at a distance of x from this, and this is the length of L total beam. So moment at the x distance from the left is mx is equal to wl by 2, which is my reaction. Ra, you can say it is Ra, you can say it is as a Rb. So that will be the Ra time x minus w x square by 2. So what is the my equation? Bending equation for the deflection, that is the d2y over dx square is equal to m over ei. So what is, I have put this value for the m, I have put this value here, and ei I have taken it to here. So this is my equation for the deflection. If I will integrate it, then I will get this equation, wl by 2 x square by 2 minus wx cube by 6 plus c1. So this dy over dx, what it represent? It is represent theta, slope of the system. If I will again integrate it, I will get it terms in the terms of y, and again if I will integrate it, x square become as x cube by 6, and x cube become as a x cube x4 by 4. So that multiplication will 24, plus this will become as a c1 into x plus c2 into c2. So that is my deflection or the displacement, span displacement. Now I need to apply the boundary conditions. So for this case, let us say my displacement is this. So 8x is equal to 0. My displacement y is equal to 0. And when my, at the mid span, I know at the mid span my displacement would be the maximum. So at that point my slope is 0. Theta is 0 at x is equal to L by 2. Okay. So these are my boundary conditions. X is equal to 0, y is equal to 0, 8x is equal to L by 2, theta is equal to 0. So now apply these. First let us apply it at L by 2, at x is equal to L by 2, theta is 0. So put these equation in this, put this term in this equation. So if I will put this equation, 8x is equal to L by 2, dy by dx or theta becomes 0, that x is equal to L by 2. So I will put the value of x, then I will get the C1 is equal to minus WL cube by 24. Now if I will put the 8x is equal to 0, y is equal to 0, which leads to C2 is equal to 0. Like all the coefficients has contain the x variable. So if I will put the x is equal to 0, so C2 is automatically become 0. So what will my equation become? These are the previous one, and that is a C1. Okay. So this is my equation for the uniformly applied load. Now what will be my maximum deflection at the center? Because what is my shape function? Shape function is the displacement at x distance divided by the displacement, maximum displacement. This is my shape function. So y max, maximum displacement at the mid span. If I will put the x is equal to L by 2, I will get the my max is equal to minus 5 by 384 WL4 divided by the EI. And if I will divide it, like put this value in this one is this, and this is that. If I put it, I will get the shape function as a psi x is equal to y divided by y max. So that is my shape function. Is there any doubt in this question? Anyone? If not, then let us move to the further question. In this, a uniform cantilever tower of length L has mass per unit length is equal to m, like the unit is kilogram per meter, and the flexure rigidity is given EI. Assuming the shape function is given to you, psi x is equal to 1 minus cos pi x by 2l, then what would be the equation for the generalized stiffness for the continuous system? Like for the formulation ways, if you have gone through the NPTEL 7th week content, you can find out the formulation for this generalized stiffness in the continuous system. So the generalized stiffness of the system is given as a k bar is equal to integral from 0 to L EI and double integral of the shape function, and then do the square of it. So first the shape function is given as a psi x is equal to 1 minus cos pi x by 2l. If I integrate it, like differentiate it, first differentiate it for phi dash x, that is coming out pi by 2l into sine pi x by 2l. Then again differentiate it, that is coming out to be pi by 2l square cos pi x by 2l. Now I just need to put it into this. Can you put it and can you try? Anyone? Like what will be the stiffness? Like you just need to integrate it. So if you will put the equation in this, so the final solution is coming out to be this EI is equal to, this is your psi double dash x, and if we integrate it, we will get this 3.04 EI by LQ. So this is the stiffness of your cantilever tower. Okay. Now we are moving to the longer question of the continuous system. In this question, a reinforced concrete chimney 200-meter height has a uniform hollow cross section with outside diameter is given as a 16 meter and the wall thickness is given as a 1 meter, like as shown in this figure. 1 meter shown in the figure. For the purpose of the preliminary earthquake analysis, the chimney is assumed clamped at the base. Chimney is fixed at the base. The mass and the flexure rigidity are computed from the gross area of the concrete. Like we are considering the reinforcement is still is not there, and the damping is estimated as a 5%. and the unit weight of the concrete is given as a 2400 kilogram per meter cube, and its elastic modulus EC, E concrete is 25,000 MPa. Now, assuming the deflected shape function due to the lateral force at the top, like the shape function is given to you as a 3 by 2 x square by L square minus 1 by 2 x cube over L cube. So, estimate the peak displacement, shear force, bending moment for the chimney due to the ground motion characterized by the design spectrum, as the peak deformation is shown. Peak is acceleration is scale to 0.25. Like we have to do the same steps which we have done in the question 3. Only thing is that this is the continuous system. Okay, so for this, like, do you have you understand the question, what we need to calculate, how do we do? Is there any doubt in the understanding of the question? Okay, if not, then move to the question. First, calculate the properties of this chimney, such as a mass and the generalized mass, generalized stiffness, load factor, and the so the chimney properties. First, the length of the chimney is given. Length here, the length meaning the height is given as a 200 meter. So the cross sectional area is A is equal to pi r naught square, r outer square minus r inner square. So outer is given as a, like, the outer diameter is given to you as a 16 meter. So thickness is given to you 1 meter. So the inner diameter will be the 16 minus 2t, so that would be the 14. So the the radius in the outer radius is 8 meter, and the inner radius is the 7 meter. If you will calculate the cross section area, that is coming out to be 47.123, and the mass per unit length is, like, the you have given the density as a 2400, gamma c is given to you 2400 kilogram per meter cube. Okay, and the area you have calculated, so that mass per unit length is coming out to be 2400 into 47.12, that is coming out to be 113,088 kilogram per meter. Now calculate the second moment of inertia I. So for the section, what will be the value of, like, the for the circular section, like without hole, what is your I? It is the pi d4 by 64. So for the hollow section, we will, like, minus the inner section, this section. So if we converted it into the radius, so that is d is equal to 2r. If we do the 4 time, then it is become as 16r 4. So we take as 16 as a outside from both outer and the inner, and if that will be cancelled out, this that will come as a 4. So that is the pi by 4 r naught 4 minus r inner of 4. So if you will put the r naught as a 8 meter and r inner as a 7 meter, you will get as I is equal to 1331.25 meter 4. And the flexure rigidity, you can calculate EI is equal to 25,000 MPa. So if we convert it into the Newton per meter square, that will be the 25,000 into 10 raised to power 6, and the I is given to you 1331.25. So that is why EI is coming out to be 3.328 into 10 raised to power 13 Newton meter square. Now calculate the generalized properties of the continuous system. So for the generalized properties, meaning the M equivalent, M generalized, K generalized, and the load factor, gamma. These three are the properties. So first, M generalized is integral 0 to L mx psi x whole square dx. So what is your shape function is given to you 3 by 2 x square by L square minus 1 by 2 x cube by L cube. If you put the mx value is, mx value is this, like whatever we calculate here, put this here. Shape function is given to you in the question, and the length is given to you 200. So if you will do the integral by using calculator, you can use. we are getting this much of the mass. Okay. Now calculate the stiffness. So for the stiffness, 0 to L EI psi double dash x square dx. Like this formulation we use in the last question also. So that is become as a 0 to 200.
Sir, previous slide, please. 1 minute.
Okay. Yes. Any doubt? Is there any doubt or like you are writing something?
Yes, I wanted to see the M dash
Okay,
again.
calculation. Okay, okay. So is it the same whatever you are whatever you get?
I'm not calculating. I wanted to just see that
Okay.
again.
So can I move to further slide? Next
Okay.
slide.
Yes, sir. Yes, sir. Yes, sir.
Okay. So now the stiffness. For the stiffness, we have discussed that expression in the last slide. So for this, 0 to L EI psi double dash x square dx. If I put the value of EI and the shape function and do the integral 0 to L, I got this kind of, this is the my stiffness in this. Now I will calculate the L factor, which is 0 to L mx psi x dx. So that will become as a same, put the value of mx whatever we get in the last slide, and this is your shape function. So I got this kind of L factor in this. So now the time period, you can get time period omega is equal to square root of k by m. So that will be the natural frequency omega. Now the time period is 2 pi square root m by k. So m is in the last slide and the k is whatever k we have get it here. Put this here. So here we are getting the, my time period is 4.10 second. Natural frequency 2 pi by tn, that is coming out to 1.53 radian per second. Okay. So now the peak value of acceleration, you can calculate the peak value of acceleration. Tn is equal to 4.106. So can you tell me what is the SA by G for 4.106? Anyone? For Tn is equal to 4.106, what will be the my pseudo acceleration? SA by G. For, if not, that my Tn is lies in this range, this range. So my SA by G would be the 1.8 divided by the Tn. So SA by G is coming out to be 1.8 divided by the Tn. So SA coming out to be 1.8. Put the value of Tn here, this one, and multiply it with the 9.81. So that is 4.3 meter per second square. Now the peak response is scaled to 0.25 G. So SA is scaled to 0.25 times 4.3. So that is become 1.075 meter per second square. Now for this, we have to calculate the gamma as well as, so to multi getting the dynamic to take the effect of the structure, mass variation of the mass, so that is a L by m. You can call it as a partition factor in the further chapters. So L and m equivalent we have calculated in the last slide, so that gamma factor is coming out to be around 1.6. So our peak displacement of dynamic response is that knows it gamma into d, so that is become 1.59 into d. How d? This is my acceleration and this is my omega n square. Like omega is the 1.53, so if I will square it, so I get this z naught at a 73 centimeter. So now I can calculate the peak displacement of the tower, which is u naught x is equal to psi x into z naught, which is coming out to be Z naught is 73, and this is my shape function. So you can calculate the displacement at any location of the chimney. If you will plot this equation, you will get this kind of scenario. Like this is the u naught x, and this equation is this. So maximum deflection 73 centimeter, and if you plot this, you will get this kind of curve. Now determine the equivalent static force. Like for determine the shear, determining the bending moment, we need to first calculate the equivalent static shear force. So for equivalent static shear force, whatever formula we have discussed in the lumped mass, that is the same. F naught x is equal to gamma mx psi x a. So gamma is what is gamma 1.59. Mass is given to you. Shape function is this one, and the acceleration is 1.075. So put this value in this. Gamma is 1.5. Mass is this 113088. This is my shape function. This is acceleration. So this is the expression for the equivalent static force. So now you can calculate the equivalent static force at any location. So this is the your expression for the equivalent static force. Like it's the top to bottom, and the if you will put the x is equal to L at the top, the equivalent static force is coming out to be 193.3 maximum force. And now this is your equivalent static force. Now if you need to calculate the shear force, if you want to calculate the shear force, let us say this location above this, let us say this is the x test location. So what we do to just integrate this force, you will get your shear force at any location up to this. If you want to up to this, then do the integral up to this, says like y f naught. So integral from, says this is my x naught x test, from x test to 200, or integral of f naught x dx. So this will directly give me the shear force. Okay, so for the shear force, so this is the x I written is as x to not confuse. So you can take it as x test to L f naught x dx. So at the shear force at the mid height, says x test is equal to L by 2. So that will be the L by 2 x dash, and that is a f naught. If you will integrate it, you will get your shear force 12,383 kilonewton. If you want to calculate the shear force at the base, this will become as 0 for the base. So this is your expression for 0. If you calculate this, you will get this expression 14,497.5 kilonewton at the base. And this is your the plot of the shear force at different location. Now, if you want to calculate the bending moment, for the bending moment, what was your like this is your says force F naught x. If you want to take the calculate the bending moment at this term, then this load, total load, this multiply the center of this, or the like the in this we are doing the integral. So multiply this the whatever the distance, whatever the center of distance you will getting. So for the bending moment, x is the location from where you want to get the bending moment. Says as the mid span, for the mid span, that is the L by 2, and says like this. This is your says x something x here lies. So that will give you the lever arm x minus x dash is your lever arm. If you will multiply this total load to this lever arm, you will get your bending moment. So x dash is the location of the bending moment. So bending moment is the mid height. If you will calculate, so that x dash become L by 2. Same this one. So this is our lever arm. This is our force 193 into this. And then if you do the integral of this, you will get your at L by 2, that is 100. You will get your moment. This much of your moment, 7.3 into 10 raised to power 5 kilonewton meter. Now, if you want to calculate the bending moment at the bottom, at the base, this will become your 0, this term, and this x dash also becomes 0. So, this is my expression. If this is 0, and this is x is the lever arm, and this is your f naught x. And if you do the integral, we get this solution. This much of the bending moment. This is the expression for the bending moment power. These are the six questions we have discussed. If anyone has any doubt, is there any doubt? Anyone? In any six questions you have doubt? Like these six questions are similar kind of questions, which will help you to solve the assignment of the week 7. Like same procedures, like only the mainly difference is the, like in the some sort of, here we discuss the 5 story, there will be 3 story. Here we are discussing chimney, there can be another kind of cantilever or something else. So is there any doubt, anyone? Am I audible to everyone?
Yes, sir.
Is there any doubt?
Sir, uh, that story drift is the relative displacement relative to what? Which story? Bottom or topmost story?
Drift is like is the, like only that story, that like it is not containing the other story displacements. Like if you say, like you have the 3 story,
Okay,
let us, if you have 3 story, say this one. So like my displacement is a whole, this one is the my displacement of the overall. Now the peak drift is, let us say, u3, u2, and u1 are the displacement. Now for the peak, u1 is same. For the u2, the drift will be u2 minus u1.
okay,
Okay.
okay, got
And for this,
year,
u3,
year 3 minus year 2.
u2. So that is the relative to the their base, or like previous one, you can say it.
Okay, previous one. Okay.
So that way you can consider it as a,
Okay,
like whatever displacement is present, like you are considering diffraction from this year only. If you have like the study the p delta effect kind of,
okay, okay,
so that is the your drift of the particular story.
okay.
Is anyone has any doubt in any other questions? If you don't have doubt, you can leave the session. I'm here for further 5 minutes.
Sir, are you going to solve any in future any problems relating to machine foundation design?
No, in this course, like we are restricted to the, like buildings and the all the, like the machine foundation, we have calculation and all this. That was in the prior cases when we have transmissibility or some, like the response reduction factor. Now we are not going to solve the some machine related foundation, machine foundation related one. Only the, like the buildings, like stories and all this stuff, can towers and all.
Any water tanks or involving some convective and impulsive mass, this kind of any problem? Are you
No,
going to solve?
no, no. In this course, that has not been covered for the impulsive and the that part. That topic is not considered in this NPTEL course.
Okay, okay, sir. Thank you.
Is anyone has any doubt in this session, or should I conclude the session?
No, sir. Okay.
Okay, if you have any doubt in this session, you can ask it to the discussion form or in the next session.
Sir,
Okay. Yes.
I actually had put a doubt in the discussion forum, that Google form, that is it possible for you to conduct after 7, sir? After 7 p.m.?
No, actually, that session is like we have given that session initially to the NPTEL team. So now I can conduct, but they can't change because like they have fixed that schedule. NPTEL, we have given the slot. So now this is
Okay,
not
okay.
like from my side there is no problem, but NPTEL is not flexible to changing the schedules because that affects the other also.
Okay, okay. Because now also I have joined from my office. So
Okay. So you can like you can pass this in the like the YouTube whenever I upload, and then you can ask the questions in the next session if you have any doubt, or you can ask to the discussion form also.
okay, okay, sir. Got it.
Okay.
Thank you.
Whatever your doubt, you can put in the discussion form, so I can discuss these doubts also here. So you will be able to
Okay.
like you look at your doubts.
Okay, sir. Okay. Thank you.
Okay.
Sir,
Okay.
sir,
Thank
we
you.
have doubts for especially when this structure is coming in contact with the soil, like how to calculate soil springs, or if it is a pile, spring value for piles. Because nowadays we are modeling all these things in software,
Yes.
and that's interface is now actually to work in office, that is more critical.
Soil structure interaction.
So that is not
Not
considered.
exactly short-term interaction, but basics like while designing machine foundations, block foundations, embedment, soil embedment effect, and like we calculate various values of coefficient of uniform compression, non-uniform compression, shear, non-uniform shear. This concept and any problem on this, if any solved, if we can share as a PDF also, will be helpful. Like how it is done in a, because it is all done in software in office, but we don't know how it actually works in the depth. Like it is a time domain. We say that it is a response coming from time domain,
Yes.
but
Yes.
you have explained as Duhamel's integral, convolution integral.
Yes.
But how these things are actually done, like central, you have told us some central difference method, Newmark's method,
Yes.
but
Yes.
how these things are actually calculated for machine foundation, like compressor foundation or some centrifugal, this kind of a thing is very useful in our office work. Like we are doing, but in depth we don't know.
Okay, like in this course that part is not covered related to the like from the below the foundation, that part is not covered. So like in the foundation part, but if I found any document related to this, I will share definitely with you.
That will be great. So thank you.
Okay. Is there anyone has any doubt, or should I conclude the session?